Yeah, thanks, Ayush. So yeah, Ayush, well, I was going to give another talk, but then he said that if I come to Aalto, I have to give a talk on GPs. So I'm giving a talk on GPs. So the main topic of today's talk is going to be about some of the issues that can arise in Gaussian process regression in the presence of model misspecification, which typically will mean in the presence of things like outliers. And there's really quite a lot of methods that have been developed for this problem. Um, and the problem is that a lot of these make your computation quite a bit harder than if you try to kind of take into account these outliers. And so it really slows things down for your algorithm. And so a lot of people tend to just ignore some of these outliers or do kind of slightly more hacky things to remove them and then run their GP. And so what we've proposed is a line of work which is about how to do GP regression, not in a Bayesian way, but in a generalized Bayesian way. And if you don't know what that means, I'll explain shortly. But that allows you to do kind of rigorous GP regression, provably robust, at the same cost as you would do standard GP regression. And so this is really a line of work that's been pushed by my PhD student, Matthias, who wrote the first paper on this last year. And now we've got a second paper, which just was accepted to ICML with my other PhD student, William, who just started a few months ago. And so this is also in collaboration with Jeremias, my colleague here at the bottom left, who's co-supervisors for both Matthias and William, and our collaborator, Andrew Duncan at the Alan Turing Institute. Okay, so I sort of was hoping that most people knew about GPs, and from what I can tell, this seems to be the case. But just to kind of fully clarify what I mean by GP regression, what I mean is I'm going to have a setting where I have some pairs of covariates and responses, so xi, yi. And I'm going to assume a model which is of this form. So I'm assuming I'm observing some function of the covariates up to some additive noise. And typically when people say GP regression, what they mean is they're going to assume a GP prior on a Gaussian process prior on the function f. And typically they will tend to assume something like normal 0 sigma squared on the observations. Okay. Now, why Gaussian processes? Well, most of you seem to know about Gaussian processes, so I probably don't need to go on too long, but there's a few reasons. So the first one is that they're a very flexible and interpretable model. So by picking a mean function and a covariance function, you can input a lot of properties that you think your function might have. So if I think that my function is very smooth, I can encode that through the mean and the covariance. If I think it's periodic, I can also do that, sparsity, et cetera, et cetera. And so whenever I have some prior knowledge, I can go and play and input that into ever more complicated means and covariance functions. It's also a non-parametric model, so I know I can approximate many things. It's got a Bayesian flavor, so here I'm going to work and try to compute my posterior. And so if you're a Bayesian, you like this, so you can specify all your uncertainty through the prior and then update that with observations. But mostly the kind of main reason that people like this for regression is that you can do exact conditioning. You can do Bayes exactly in closed form. So if you start with a Gaussian process, you update with Gaussian likelihoods, then you're going to end up again with a new Gaussian process, and you have a nice formula to kind of get the posterior mean and the posterior covariance. And that's really the really nice thing about this is that it's very computationally tractable. You don't need to worry about MCMC, variational inference, or whatever. At least it's in its most basic form. Okay. Now, let me just kind of give you a little sketch of what's the sort of problems that we're going to try to tackle are. So imagine you have some function here, which is this dotted line. You have some observations, which are kind of a bit shifted by this noise. So I could use a GP. Here I'm just plotting the mean, and it's very good because my model is very flexible, et cetera, et cetera. So that's the sort of pictures that you'll see in GP talks. But then the problem is that in the real world, in kind of quotation marks, what might happen is you might have some sort of extreme observations, say outliers. Now, obviously here, my observations are very extreme, and I've made them very extreme to kind of really illustrate this problem. In reality, it's more likely that I'll have outliers which are kind of close, but not that close. And basically, the way you should think about this is that for most of my data, my assumption that the noise is normal 0 sigma squared is going to be roughly correct. But for a few observations, it's actually going to be very wrong. And these epsilon i's will take much larger values than really expected. And so if I did that and I just reran my standard GP, not taking these outliers into account, I would get something like this, where now we can see that, proportionally to the number of observations that aren't corrupted by outliers, just a few points can really drag down my line, and so I'm going to get quite poor performance. Now, obviously, this is like in one dimension, so here it's very easy. I could just literally plot my data and go and highlight it in red and remove these points and then run my GP. I could do that. But doing so in more than one dimension is going to start being a bit more difficult. And so ideally, we'd like something which can deal with these outliers without having to do exactly what I just kind of talked about. So what we'd ideally like is like a new method which can do something a bit more like standard GPs without the outliers, even though there are outliers that are there. Okay. And so the goal of today is going to be, well, twofold. So firstly, I'll talk about the paper from last year where we first introduced this method. And then I'll talk a little bit about a new extension that we have that just appeared at ICML, which basically takes this framework and extends it in the case of spatiotemporal data to take advantages of like common tricks that there are there to kind of scale the GPs, at least in terms of time dimension. And also that looks a lot more at kind of hyperparameter choices and how to kind of automate this much more so that you don't have too much reliance on that. Okay. Okay. So before I do that, I should probably review the literature on robustness and GPs. And if you just do a quick Google, you'll find a million different papers. So there's loads of different tricks, some which are just generally for Gaussian process regression, others which are more about specific applications. So obviously, one of the most well-known ones is Bayesian optimization. So there's some algorithms that are designed specifically for that. And if I was to summarize them into two parts or two categories, I'd probably do as follows. So the first category basically says, well, I know that my model for epsilon is wrong. Let's use another model. Okay, that's the sort of obvious thing. So if I think I might have quite extreme observations, maybe instead of a Gaussian, I can use some sort of heavy-tailed distribution. So this might be a student T, a Laplace, something like this. Maybe a mixture where one component is for the majority of the data, one for the extreme points. Yeah, so I'd call these kind of extended models. Then the other category is really try to detect the outliers and remove them. Now, I'm mostly going to focus on one rather than two because one is kind of harder to do in higher dimensions, but also you can always do it first and then run something like this, which does happen quite a bit. So I'm mostly going to focus on kind of discussion of these models, these methods, sorry. Okay. Now, the main issue is that if I extend my likelihood, what I'm going to end up with is something which will typically break conjugacy. So what I mean by that is that if I change my likelihood, I don't have Gaussian updated with Gaussian, that gives me a Gaussian, have Gaussian plus something else, which then gives me, well, potentially a complicated posterior. And so suddenly I don't have closed forms and I need to approximate my posterior. This is a bit more problematic, and it basically means that you have to put a lot of effort on your approximation. So there's all sorts of approximations you could think about for Bayes that have been applied to this. So you could use variational inference, you can use MCMC, etc. And basically, depending on how much you care about getting a very faithful approximation or getting a very fast approximation, you're going to pick one or the other of these methods. But the point is that all of them will break conjugacy and therefore be quite a bit slower than standard GPs. Okay. So this is an example that we've got in the paper of like a bunch of synthetic data sets. I think these are UCI data sets. And I've put the number of samples here on the right-hand side and the dimension, so they're not massive. And what I'm plotting is 3 different methods. So GP is standard GP, TGP is a standard GP with a student T likelihood, and MGP is a mixture likelihood with, I think it's 2 components. And here we just ran this with the GP flow package in Python. And what I'm reporting is the time it takes to fit the model in seconds. So what you notice is, just to pick the worst case, or one of the worst cases for the other methods, is that I can do this in 1.9 seconds for the standard GP. And this is just on my PhD student's laptop. And it's quite a bit more for the other methods. Orders of magnitude more for the other methods. Now, obviously, like these numbers might change a bit exactly depending on which package you use, which variational inference method you use, et cetera, et cetera. But the point is, it's always going to be more expensive to do this than to do standard GP regression. Okay, so ideally, what we'd want is something where you don't really pay the cost of an extended likelihood. And so very often people just ignore model misspecification. And this is purely for like computational convenience. And in fact, this reminds us a little bit of some of the earlier work in robust statistics. So obviously the field of robust statistics has existed for a long time. This is one of the kind of main papers that started it back in the 60s. And Huber is one of the main kind of proponents of this approach. So you can think of this as being robust in like a frequentist setting. This is the sort of thing that they're trying to do. And if we look at this paper, there's a few sentences which sound very similar to what I've just told you. So the first one is, Gauss was fully aware that his main reason for assuming an underlying normal distribution was mathematical, i.e. computational convenience. This raises a question which could have been asked by Gauss. What happens if the true distribution deviates slightly from the assumed normal one? So here we're exactly in the same setting, right? So it's exactly the same thing. We're working with Gaussian processes rather than univariate Gaussians. But really, it's the same problem. A lot of the time, people assume Gaussian likelihoods just because it's convenient computationally. Okay. So I'll be talking about these 2 papers. So one from ICML last year and one from ICML this year. I'll mostly focus on the first one because that's the kind of core of the methodology. And then I'll talk about some of the nice things that we've been able to do since. I know there's also other people here at Aalto that have worked on kind of extensions of this problem. So I think that's quite nice. And we're getting quite a bit of interest in this line of work. So I'm kind of hoping to kind of continue it. So we've got some plans to further extend on these papers. Okay. Okay, so let's talk about what we're actually going to do. So here, this first slide is just Bayes for regression. So it shouldn't be anything new, but it's just to kind of set my notation. So what I care about is the function values are a set of points x. I'm going to create a posterior from a likelihood and a prior. And here I'm going to have everything in vectorized form, just for simplicity. Now, what we're going to do is something a little bit different. We're not going to do Bayes, we're going to do generalized Bayes. And generalized Bayes is a kind of a line of work which has existed for a little while under various names. So maybe you've heard of quasi-Bayes or Gibbs posteriors. There's a few different names. But the idea is that you're going to update your beliefs, so update your prior, not with a likelihood, but with something else. And this something else typically takes the form of exponential of minus some loss function. Okay. And now, obviously, I'm going to kind of motivate this a little bit in the next few slides, but now you get a new quantity, which is again a distribution on the quantity of interest, which is called a generalized posterior. Okay, so let's think a little bit about this. So firstly, why can I call it generalized Bayes? Well, the first one is that if I take my loss to be minus 1/n the log likelihood, then I recover Bayes. Okay, so that's kind of straightforward. And of course, we all get drilled into our head that Bayes is the optimal way of updating beliefs, etc., etc. But something which is important to remember is that this is only true if the model is well specified. So if your model is right, the best thing you can do is update with Bayes' theorem, i.e. with your likelihood. But when your model might be a little bit wrong, like in our setting, this might not be the case, okay? And so it's basically motivated a whole line of work which has thought about what can I do in terms of changing my loss function in order to do good updates when my model is a little bit wrong. Of course, if it's completely wrong, then I have no chance of doing anything, right? But if it's only a little bit wrong, maybe I can kind of mitigate some of the impacts of the type of things that are wrong, for example, the presence of outliers. So if you want to learn a bit more about generalized Bayes, I think these two papers are probably a good starting point. And they really justify, or think about the sort of properties that you want from your loss function. What I'm going to do in this talk is I'm going to mostly focus on the loss function, which is going to be convenient because it's going to give us some form of robustness to mild model misspecification. And it will take the form of a statistical divergence between my observations and my model. Okay. So this is very common in the literature, and there's still the question of how do I choose this divergence? But at least intuitively, what you can think of here is that, if my model looks a lot like my data, then in terms of this divergence, then I want to push my posterior in that region, and this is what's happening because I'm taking exponential of minus this loss function. But obviously, depending on which divergence I pick, what I mean by similar will be slightly different. Okay. So usually people just choose this divergence for robustness purposes, and we're going to choose it both for robustness and computational convenience. Okay. So the type of divergence that we're going to look at are score matching divergences. And I'm hoping that quite a few of you have heard of these. So it's been around for a little while in machine learning. It's become extremely popular now with diffusion models, as that's like one of the core tools to train diffusion models. And the idea is quite simple. So you just basically compare two distribution in terms of the gradient of their log densities, which is called the score. And so when the scores are similar, I'm going to say that P and Q are similar. And when they're quite different, I'm going to say that they're quite different. Okay. And so at least if you don't know about score matching, you'll probably know that we can identify distributions through their densities. So if two densities are similar, the corresponding distributions are similar. Here it's a similar idea, except I'm working with scores as opposed to densities. So just a little picture. So if I have the score, so here SP would be the score of P and SQ the score of Q. You can see what this looks like. So this would be in one dimension. So here, these are functions. So they depend on y, or I've put x here, but it should be y. And so what you do is you average out the difference in scores, and that's what the expectation on the outside does. So I measure the average difference between score functions, and that tells me how far P is from Q. Now, what we're going to do is look at a weighted generalizations of score matching that we introduced in this paper, and we call this diffusion score matching for reasons that I won't really go into, but you can just think of it as a weighted score matching, where my weight is essentially saying there are some regions of the space where I care about my scores matching more than others. Okay. Okay. Now, so score matching, this is for kind of marginals. Here we're going to work with regression models. So we're going to work with conditionals. So we need a small extension, which is basically do score matching and then average out over the conditioning variable. So all that's happening is just this extra expectation on the outside. The expression looks a bit more, ugly, but this is all that's happening. Now, in score matching, the kind of trick is that you can do some form of integration by part. And this gives you a term which now only depends on the score of P with an outside expectation in Q. plus a constant term which doesn't depend on P. Now, and so I can approximate this expectations with the data I have. So if I calculate the divergence between P and some samples, what I get is some sort of Monte Carlo estimator of this expectation. So in our case, these grad log P, these will be the scores of the likelihood. And so we can just go on and start using this within our generalized Bayes framework. So let me just kind of give a few more formulas. So remember, I keep on saying that GPs are conjugate. So I haven't actually showed you this. So in GPs, usually the sort of formula for the posterior will be something like this. So I have my posterior is going to be Gaussian with a certain mean and a certain covariance, which depends on my prior mean and my prior covariance, and of course my observations. So if instead of doing standard GPs, I update not with my likelihood, but with this score matching divergence, I'm going to get something extremely similar. And so let me just highlight in blue what differs. So the only thing that will change is these terms in blue. So one is this M term, that's the prior mean, a vector of prior mean evaluations at the data point. That now becomes that same vector plus an extra term, which depends on the weighting function. And then this matrix, which is normally a diagonal, so an identity matrix, sorry, becomes a diagonal that depends only on the weight. So at least purely from the formulae, you can tell that computing this or computing this will be about the same cost, right? It's just that now we have this extra complexity of having a weight function that we get to play with. And this weight we've inherited from the score matching divergence. Now, this weight isn't just a small cute thing that comes out. It's actually going to be the crucial thing that's going to allow us to get the robustness element of the method. Okay, so here I've just put it again, so we have all the formulas there. So if I take a weight which is constant in x and y, I've just picked a constant conveniently, then I recover exactly standard GPs, okay? So again, we can think of this as some sort of generalization of standard GP regression. If I pick the weights depending on only x, but not y, then I'm going to recover what's called heteroscedastic GPs, which is what you get when you have GPs with varying variance term across covariate space. And when we choose W to depend on both X and Y, we get something that doesn't really exist, but that will be able to give us some form of robustness if we pick our W in a sensible way. Well, at least that's the claim that I'm making now, and I'm hopefully going to show you this over the next few slides. Okay, are there any questions so far? Yeah. Sorry? Shouldn't W just be 1? Yeah, maybe I've rearranged my constants wrongly. It's possible. Yeah, anyway, so it's constant and you recover standard GPs. Yeah. Okay. Okay, so in terms of the weight function, the sort of weight functions we're going to pick are going to look like this. So if I just give you this formula, it's going to look a bit, well, weird at first, but maybe if you're used to working with GPs, you can recognize this as looking like an inverse multi-quadrate kernel, evaluated at y minus gamma x. Okay, so if I fix one value, one of the inputs, let's say y, what I'm going to end up with is some sort of bump function, which is basically saying, sorry, this should be gamma x. So if the y that I observe is far from gamma x, it's going to have a smaller weight, okay? So what I'm trying to do is saying if I see observations which are extreme, I want to downweight them because I don't want to be impacted too strongly by outliers. And so here by far away, it's always going to be in reference to gamma x, which we call a centering function. Now, there's a few other things we can do. So we can play around with beta that kind of moves up or down our little bump function. And we can play around with C to make ourselves more kind of peaked or less peaked, okay? And so all of these parameters, they're just parameters that, at least intuitively, all they do is they change the type of bump function that I have, and they'll impact how strongly I want to downweight outliers, or maybe not too much. Okay. So in the original paper, what we did is we picked beta to be sigma divided by square root of 2, so just a constant. We pick the centering function to be the prime mean. So we're basically saying if you get observations which are far from your prime mean, that's not so good. And we're picking C of x to be some quantile of the observed data. And the quantile, we basically required the input of a hyperparameter called epsilon, which was telling you what percentage of outliers do I expect to see. So if I don't expect to see many, I don't need to downweight a lot. If I expect to see a lot, I downweight more. Now, this has all sorts of problems. Well, firstly, downweighting with the prime mean isn't necessarily a good thing because maybe your prime mean is bad, and so you're going to get downweight some values which don't really want, well, you don't want to downweight. And this, well, having to specify an extra hyperparameter is a little bit like awkward. It's fine, you can do that, but obviously there might be some sensitivity to that. So that's what we were doing here. And so basically in practice, what's happening is you should think of the bump functions as being in this direction. So I have like a low bump. And so the things that are far away are being downweighted up or down. Okay. In the second paper, whoops, got two betas for some reason. We've kept the beta constant, but we're now using the posterior predictive to pick gamma x and C of x. So in the second paper, what we have is some sort of spatiotemporal setting where at each time point, we can compute a predictive at the next time point and use that as our centering function. That really helps improve performance. And what we show in the paper is that it really helps in terms of calibration of the model, and also just in terms of something like mean squared error. Okay. So just to kind of give you a little picture of why the second paper kind of improves on things, imagine this is my prime mean. So my black dots are the observations that I get, and some of them are outliers here. In the original method, RCGP, you can see that the red dots are actually not that far away from the prime mean, or at least not much further than the black dots. And so actually they don't get downweighted, and so they get, so actually the method tries to fit it because my centering function is this prime mean. And so it's not a very good choice of centering function, and I'm going to get bad performance. In this paper, what we do is we use the predictive. So we're here, and the next one, our predictive is going to be around here. So this is really far away from the predictive. And so that now gets downweighted, and we can see that in terms of coverage, this improves things quite a bit. Okay. So there's a few things I'm going to do next. So just to summarize what I've done so far. So what I've done so far is I've highlighted the problem of model misspecification in Gaussian processes, specifically to do with outliers. I've then proposed a method based on generalized Bayes and Gaussian processes, where by choosing a loss function in a certain way, I've been able to get conjugacy and therefore similar cost to standard GPs, and some form of robustness, at least empirically through some plots that I've showed you. And so what I'm going to do for the rest of the talk is I'm going to talk a little bit about how to actually show that this method is robust. And then I'll talk about some experiments we have. So we've done some experiments to various different problems that people typically use GPs for. So we've done Bayesian optimization, spatiotemporal GPs. We've also got an extension to SVGPs. So a lot of the things that people like to do with GPs, we can do in a kind of robust and similar cost way. Okay, so in terms of the theory, what I'm going to need is a way of measuring robustness. And here what I'm going to do is I'm going to look at the distance between my posterior and my perturbed posterior, where the perturbed posterior is just conditioned on the same observations, except I pick one of the points and I can throw it up or down. So if I go back here, you can think of it as I'm allowed to pick one of these red dots and move it up or down, okay? And so this quantity called the posterior influence function basically says how much does the posterior change if I just move up or down one of the points. So this posterior influence function is like a tool that has been used for quite a bit in various contexts to show robustness. And typically what you do is you show if this quantity is bounded as a function of the point that you get to move up or down, then you call the method robust, and otherwise it's not robust. You can also use the upper bound on this value as a measure of how robust an algorithm is. And this is all kind of analogous to what's done in more classically in robust statistics, so what frequentists do in terms of robustness, where there's this concept of influence function. So here, typically it's how much does my estimator change? Well, in our case, we have to look at how much does my posterior change. Okay. And it's fairly straightforward to show that for standard GPs, well, this is always going to be unbounded. So if I pick just one point, even if I have a lot of observations, I pick just one point, so long as I throw it high enough up into the air, very high, then I can arbitrarily badly impact my GP. Okay. So if I plot the posterior influence function, so it's a function of this YMC, and this is what it looks like. So if I take one observation and throw it very far away in one direction or the other, the posterior influence function goes towards infinity. So we've got kind of formal statements of robustness in the papers. I didn't want to like put lots of ugly math on the slide, so I've got an informal version which basically says if you use the sort of weight function that I showed on the previous slide, or well, this one is I should have changed it actually. Okay, imagine this weight function is the one on the previous slide, then you can show that the posterior influence function is actually bounded. So this is like the informal results for the first paper. If you change the weight function to the one on the previous slide, that's what we have in the new paper. And so what this shows is that basically you don't get arbitrarily impacted by just even one point. Okay. There's a few things to say about how to select hyperparameters. So obviously, the kind of typical thing that people do, and here I'm talking about hyperparameters of the kernel or the mean function. What people typically do in Gaussian processes is they maximize the marginal likelihood. And that's fine, but this sort of assumes that your model is correct. So it's maybe not ideal. So what we do instead is some form of leave one out cross-validation, which is less badly impacted by model misspecification. And with leave one out cross-validation, there's lots of nice tricks from the GP literature which allow you to essentially optimize these things essentially at the same cost as marginal likelihood. So what this does is it gives you a little bit more, well, it's not as badly impacted by model misspecification when you choose the hyperparameters. In the new paper, we also use the weights once more here, and we show that that improves things even a little bit more. Yeah, so basically doing hyperparameter optimization is not a problem for this method. Okay, so I think I have about 10 minutes. So I wanted to show a few experiments. So now I'm back to these UCI data sets. And what I'm plotting is not the time anymore, but it's the mean absolute error. And initially, I just took the data sets as they are. So I didn't inject any outliers. Later, I'm going to inject some outliers to see what happens. But when there's no outliers, or at least no assumed model misspecification, what we see is that the performance of GPs and RCGPs is roughly the same. And it tends to be a little bit better than some of these extended methods because they're a little bit harder to fit. So although they're a bit more flexible, maybe there's some error from the variational method or something like this. All we did was run it with GP flow, and there was, at least for the mixture case, some issues. Okay, now what we've done is we've then started injecting outliers. And here I have two little sketches of the type of outliers that we've injected, just to see what's the impact on each of the methods. So the first one is the so-called focused outliers. So they're all in one direction, and they're all very similar in terms of covariate space, so in X. And what we see is that our method tends to vastly outperform, well, no, maybe I shouldn't say vastly, tends to outperform the other methods. And this is actually quite reasonable because here we're putting all the outliers in one direction, which isn't going to be well modeled by something like a student T likelihood, right? So student T, you'd expect kind of extreme observations on both sides, and here they're all on one side. This one, we just added outliers only on one side, but not clustered. And here, like, we tend to do similar-ish to the mixture likelihood setting. And this sort of makes sense because actually the way we created these outliers was by adding a mixture component. So we actually generated them from a mixture. And therefore, of course, the mixture distribution is going to be quite good at in terms of likelihood. But of course, this method will be quite a bit more expensive. So we have it here. So here, this is again time now for each of the methods. So RCGP is the robust and conjugate GP, I should have said. So that's our method. So we can see that we're quite a bit faster than these alternatives and similar-ish to standard GPs. Now, the numbers are not exactly the same, and that's because the way we run these methods is by, well, we have a slightly different way of optimizing hyperparameters, and we have some sort of stopping criterion when, you know, for that optimization. So there's some differences. You know, sometimes we do quite a bit worse, sometimes we do a little bit better. I don't think these should be like overly interpreted in terms of like that difference, because at the end, the computational complexity of these two methods is exactly the same. Again, I should reiterate in terms of these other methods, the numbers that I'm giving is just the ones that we got from running this package. It could be that you can make these numbers smaller or larger by changing the exact variational inference method you use. But the point is, it's always going to be more expensive than one of these methods. Okay. So how long do I have? 5 minutes? Okay. So what we did is we then ran it on some kind of benchmark problems in Bayesian optimization. And the sort of thing we see is that in terms of regrets, so this is a problem where we've, again, injected some outliers and tried to do Bayesian optimization. You get something which has similar cost to standard GPs, but similar, but is robust in terms of regrets, or similar at least to TGPs. We then went on to do SVGPs. So now we're able to do kind of, so one thing that people like to do in GP world is these sorts of sparse approximations to go from n cubed to nm squared in terms of computational cost. And you can basically do the same thing with our method. So you then get something fast and even faster and robust. We've then got a spatial and temporal version where you can see that, whoops, oh, maybe I can't stop it. You can see that as soon as it starts seeing these outliers, so this is an example where, so this example is actually quite an interesting one. It's the Dow Jones index, where on one day, someone on Twitter said that the White House was being attacked. And so suddenly everyone panicked and started selling. So there's these sorts of actual outlier setting where you can see the price goes down, and then obviously everyone recognizes that it was a stupid hack of a Twitter account, and so it goes back up. So here you can see that standard GPs certainly struggle with this. RCGPs in this example actually does really badly because we chose the prime mean to be very low from the previous day. So this shows you again that the original algorithm we proposed had these limitations in terms of how you pick this centering function. And now with this adaptive choice of hyperparameter, with this predictive distribution, we do a lot better. So we get this kind of green line, which is clearly robust to the outliers. We have not compared to sparse GPs here. So the nice thing about these temporal GPs is that you don't need any sort of approximation and you get linear time cost. So if you're in one dimension, you can, okay, there's a few low asterisks, but in a lot of cases, you can do linear time GPs just to using kind of the time dimension is. So so you can re-implement this as like a Kalman filtering smoothing problem, and then you get linear time, which is exact. So we don't need to compare against sparse methods. And then we did also something in the spatiotemporal settings. So what we're measuring is temperature as per month. So this is a map of like the UK and surrounding areas. Every month we get temperature. Here we added some outliers for November just to see what happened. And then at the next step, a standard GP basically predicts super hot December in the UK, which is quite unusual. And then we did the same thing with these robust GPs, adding these outliers, and we see that we don't actually get impacted the next month, nor everywhere else in space. And so for these methods, what we were able to do is, again, rewrite things using Kalman filtering and smoothing to get a quite fast algorithm in terms of time dimension, but still cubic cost in terms of spatial dimension. Okay. So that's the end. So my summary is that with generalized Bayes, you can typically design algorithms which brings you some form of robustness, but also, so that's what most of the literature does. But in my view, one of the great things about it is also computational efficiency. So one of the reasons I'm here today is to collaborate with Ayush, and that's one of the things that we're exploring in kind of a completely different setting in simulation-based inference. So I think there's lots of potential to use generalized Bayes as a computational tool in various different fields. So in this example, we managed to get both robustness and conjugacy for GPs, something that no other competitor had managed previously. We could start extending to lots of other problems. So some of your colleagues here at Aalto have started doing this. I think one of the areas which could be interesting is looking at multi-output GPs, and we have some initial work in this area. But you could do this really for any type of GP which does exact conditioning, so multi-fidelity GPs, GPs with other kinds of information, et cetera, et cetera. Yeah, so I have a few slides, but I'll probably stop. Okay, I'll just show. So a few points is that you can use this sort of approach in lots of different areas. So we've done this for online change point detection, where you're trying to detect these changes without being impacted by these outliers. So this is the blue changes are when our method detects a change point. The green ones are when the standard Bayesian online change point detection detects outliers and detects change points, and you can see it's impacted by outliers. So it thinks there's change points when there shouldn't be. You can do this for Kalman filtering and smoothing. So we did that as well last year at ICML. So you'll see soon there's going to be some extreme observations which we drag down the standard Kalman filtering method, and we've got a nice robust method. You can also do this for kind of quite complicated statistical problems to do with double intractability. And yeah, that's it.